So let's start infrared spectrophotometry or spectroscopy. Infrared is related to molecular vibrations. All the molecules are having vibration, as you can see on the board that the molecule is vibrating. All the molecules always are vibrating some way or the other, rotating and vibrating, except 0 Kelvin. Except 0 Kelvin temperature, any other temperature, all molecules are always vibrating. Depending on their state, if it is solid, it will be only vibrating. If it is liquid, vibrating and rotating. And if it is gaseous, there is rectilinear motion, vibrational movement, and as well as rotational movement. All types of movement will be possible. That means it will have a higher degrees of freedom. Now this IR radiation, whenever gets irradiated onto some molecules having vibration, then that molecule will absorb that radiation. So we know carbon dioxide is a greenhouse gas. But why it is so? Because carbon dioxide has certain vibration frequency which is matching with IR radiation frequency of the sunlight. Carbon dioxide molecule has got certain vibration frequency, bending vibration, which is matching with the IR frequency of the sunlight, and that's why IR is absorbed. And as the IR is absorbed, then dissipated, the surrounding gets heated up and the global warming occurs. Got it? Molecules are having different modes of vibration. How many modes? It can be stretching and bending. Two major modes of vibration there, stretching and bending. Stretching can be symmetric and asymmetric. Bending can be different types. I will be showing you how many types of vibration there. And IR spectroscopy is related to this type of different bending and stretching vibration frequency. Why oxygen or nitrogen is not a greenhouse gas? Because these molecules, oxygen, nitrogen, okay, these oxygen molecules, oxygen and nitrogen, they are diatomic molecule. They are diatomic molecule and they don't have any bending vibration. They have only stretching vibration. Hey, mobile rakho. So mobile, this particular mobile chillers, stretching vibration and bending vibration. These two types. Okay. Now stretching means just like a spring. You have seen spring. How the spring is reacting. It is either getting stretched or getting compressed. Again stretched, again compressed. That phenomena is happening for molecule also. That is stretching. And this stretching can be symmetric as well as asymmetric. Symmetric means both the sides, suppose triatomic molecule, CO2 triatomic molecule, carbon at the middle and two oxygen at both the ends. O double bond, C double bond O. That is the structure. Now stretching. Both the oxygen is going away equally and then coming back equally. So that will be called symmetry. On the other hand, one oxygen going away, other oxygen coming in, compressed and elongated at the same time. One side elongated, other side compressed. And then the opposite one, this side elongated, this side compressed. So this way if it happens, it will be called asymmetric stretching. So stretching can be symmetric, asymmetric. And then bending. Take a triatomic molecule. It can have a bending like this. Suppose this is a triatomic molecule, this is one atom, and at the center there is another atom. So the molecule is doing like this. This is called scissor action. How do you use scissor? So this is called incision. Scissor action, this particular vibration mode is called incision. Now the molecule can vibrate like this. Different way of vibrations are there. I will be showing that. Now this is, suppose there is a spring and at the end of the spring there are two balls. Ball spring system. And molecules are actually behaving like a ball spring arrangement. That's why this is, we are drawing the analogy with the ball spring. This is spring attached to two balls. Now frequency, that wave number of this movement, stretching movement, is 1 by 2 pi c root over k by mu. Mu is this is characteristic vibration and relationship. This is the relationship. What is mu? Mu is the dipole moment. and K, it is a constant, proportionality constant. Okay? Spring constant, proportionality constant. Dipole moment. Dipole moment. Molecular dipole moment, which is in this case. Now spring constant, for a spring ball spring, there is a constant, and if it is a for molecule, then it will be dipole moment. Now this IR region we can divide into certain category. 780 to 2500, this is called near IR. 2500 to 25000 in micrometer unit. Okay, what is the unit of ultraviolet and visible? Yesterday we discussed, it is nanometer unit. And this IR frequency or whatever, always in the range, micrometer unit is used, micrometer, because it is in a different region. So micrometer. So 2500 to 25000, that is the wave number. And in case of IR, wave number is mostly used, and wave number is directly proportional to energy. More the wave number, more is the energy. Okay, wave number, energy. So these are the different groups present into the molecule. Functional groups, we call them. Depending on the functional group, the property of the molecule will vary. So these are the functional groups. And the wave number of the spectrum, wave number that we obtain in the spectrum will be in this. These are the values. There is a range always. Why? Because there is always some environmental influence. Environmental influence means, suppose you have C111N, but this C111N may be attached to a benzene ring. It may be attached to a chain. Depending on that, there may be slight variation. Okay, just like in the UV, we are getting a peak. In IR also, we are getting a peak, but inverted one, because here we are plotting against wave number. So then the UV plot, I have shown you the UV plot something like this, but IR plot, it is just reverse, because here we are plotting the wavelength lambda, and here we are plotting the wave number 1 upon lambda. That's why the plot is entirely different, looking different. Okay, but what is the objective? That is same, to find out what are the different function groups present in a molecule. To find out different function groups present in a molecule. That is the purpose. And in case of UV visible spectroscopy, we are getting the information like molecular double bonds, position of the double bond, number of double bond, conjugated, non-conjugated, diene, etc. Mainly this double bond, triple bond phenomena is very important in UV. That type of phenomena, chromophore, molecular chromophores present or not, oxochrome, chromophore. Oxochrome and chromophore, I think ultraviolet spectroscopy I have not discussed yesterday, so just talk a little bit. I have shown you something. Okay, yesterday, oxochrome and chromophore. Some groups are there, they are called chromophore groups. Okay, just give the heading chromophore and oxochrome. I will explain to you. But that is under UV. So, what is oxochrome and what is chromophore? Chromophore means a group that is imparting color to a compound. Originally, the compound is colorless, suppose. Okay, originally, suppose the compound is colorless. Now, we are introducing certain group. And after that it is found it is giving some color. Like benzene is colorless, put nitro group, nitrobenzene, colorful. So some color is coming due to nitro group only. So this group will be called chromophore. Understood what is chromophore? Achha. Now, if we give another group, we insert, that is changing the color. Not giving color, but changing the color, intensifying the color, or reducing the color. That type of phenomena. That is called oxochrome. So you know auxiliary means? Auxiliary means what is auxiliary? Something additional. So oxochrome is also the same. It is also something extra, some additional thing, which is modifying the color, which is intensifying the color. Okay, it is shifting the position of the lambda max. some little bit of change it is doing, that is oxochrome. But if you just put only oxochrome, it will not give color. But if you have chromophore, then you have oxochrome, it will give some color. Like for example, another analogy I will draw. You have a catalyst that is enhancing the reaction. How you can improve the quality of a catalyst? That is called promoter, isn't it? So secondary is something we are adding, that is called promoter, which is promoting the activity of the catalyst. So here is also like that. You can draw the analogy like that. Chromophore is a group that is giving color to the molecule. Now another group I am incorporating, which will give some intensify the color or reduce the color or change the position of the color. And position change means color change also. Suppose originally it was yellow, now it is showing orange. Little bit of shift. Sometimes drastic shift, sometimes little bit of shift. That may happen. That is called oxochrome. Okay? Now, the shift, as I talked about, shift, the lambda max shift. If the shift is happening towards higher energy, it is called blue shift or hypsochromic shift. Okay? If the shift is towards higher energy and shorter wavelength, higher energy means shorter wavelength, then the shift is called blue shift or hypsochromic shift. And if the shift is shift of what? Lambda max. What is lambda max? The maximum intensity of absorption. The wavelength having maximum intensity of absorption is called lambda max. The wavelength having maximum intensity of absorption called lambda max. Acha, if you are not sure, I will clarify. Acha, suppose there is a peak starting from here, but from here to here there is everyone, there is absorption. But where you find the absorption maximum? It is here. The corresponding wavelength is called lambda max. You have got a peak. You have got a peak. Peak is starting from a point and ended at another point. In between there is a range. Within that range absorption is happening. But within that range a particular wavelength we can mark where the absorption is maximum. That is lambda max. Is the lambda max clear now? Now the shifting of lambda max I am talking about. The lambda max is shifted either left side or right side. Left side means higher energy, lower wavelength, smaller wavelength, and right side shift means towards the longer wavelength. So if the wavelength is shifting of wavelength towards shorter wavelength, it is called blue shift. And if shorter wavelength means left side shift, it is called blue shift, because lambda we are plotting against lambda. So shifting towards left side means what? Shorter lambda, that is higher energy, it is called blue shift. And if the same thing is happening in the right hand side, shifting in right hand side, it is called red shift. Okay? Red shift, blue shift. So this thing happen. So that is our objective in UV. But what about IR? In the IR, we get here different function groups. But why there is a range always? Because this molecule, this particular group, it is not alone. There may be other groups also that will influence. So little bit of influential change. Because of the presence of other groups, this particular group can shift the position little bit. Here also, little bit of shifting of position. So that is called, that's why there is a range. It is 2260, 22220. Acha, this C double bond O, carbonyl group, aldehyde ketone. Acha, aldehyde ketone, see the range 1780 to 1650. Now this C double bond O may be present into alkyl group, it may be present in aromatic compound, benzaldehyde. You will get different value, not exactly same value. Little bit of change. That's why always the range is given. Got it? And intensity, whether strong and weak absorption, whether the peak will be quite deep or not that deep, that depends. That intensity means if the intensity is high, the peak will be at that position quite deep, quite down. Okay, up to certain depth it will come down. But if the intensity is very small, then the peak will come down a little bit. Okay, so that is written here. The intensity, medium to weak, strong. Okay, so different function groups is giving this absorption in different position. So if I can get a spectrum, if I can get a spectrum, from that we can analyze that what are the function groups may be present in that molecule. Okay, what are the function groups supposed to be present in that molecule? Suppose you are getting a peak around 3000. What do you expect? You are getting a peak, broad peak around 3000 centimeter inverse. That means there is some OH group present. Okay, and OH group will give a broad spectrum always, not very sharp peak. But C double bond it will give a very sharp peak. So that will give guaranteed. It will give guarantee. Okay, you are getting very sharp peak around that 1760. Then you have got C double bond group. From that way, from spectrum analysis, we can decide what are the groups present in a molecule, and that is quite important information. From that only you can decide what type of molecule is present into this that drug or some food sample. Okay, you can analyze the food sample. What type of preservative is used? How much preservative and what type of preservative you want to know? Okay, you know what is the preservative used for into food? Sodium benzoate. Sodium benzoate is one of the preservative. So this type of preservative, how much preservative is given or added to my food? Preservative is bad for health, na? Preservative is not bad for health because these are chemicals, and most of the chemicals are bad for health. So this chemical, particularly this sodium benzoate, should not be very high quantity. To prevent bacterial contamination, we are using this, but it will damage our good cell also into the body. Okay, it may damage the kidney, it may damage the liver, isn't it? Internal organs. That's why it should not be in a very high quantity. Now you have got a doubt that this particular unknown, some packet has come in the market, how much preservative they are using. They will always claim the best. But if there is a testing required, then IR spectroscopy, UV spectroscopy, this can help a lot. Not only molecular and mechanism and molecular structures, okay, but practical application is also there. Broadness. Actually, that voice is giving different type of vibrations. Lot of vibration present, and vibration is always giving broadening. More vibrations will give more broadening, and rotation, vibration, all these phenomena is giving the broadening. And you see, these are the molecular vibrations. These are the different type of molecular vibrations. I told you already, symmetric stretching. This is symmetric stretching. Symmetric stretching means both the blue ball is coming closer and going away. That is symmetric. Achha, scissoring action. That is also symmetric. Achha, now this waking action. This is also symmetric. Both are coming away and both are coming closer together at the same frequency. Always it is coming, doing like this. So then it is symmetric. Now this is asymmetric stretching. One coming closer, another going away. So this is asymmetric stretching. This is rocking and then twisting. These are bending. Bending modes of vibrations. Okay. So stretching and bending. These are the two major modes. Stretching and bending. Stretching can be symmetric and asymmetric, and bending can have four types: rocking, wagging, twisting, and scissoring. Alright? So these four types are there for bending, and stretching, symmetric and asymmetric. And this is for triatomic molecule. If you take diatomic, there is only stretching. There is no symmetric, asymmetric, there will be no bending also. But rotation possible. For diatomic, there are only two modes. One is stretching vibration, and this is rotational vibrations. Okay, rotation and vibration. These are two types: rotation and vibration, and vibration will be stretching vibration only. That means modes of vibration will be very limited, only one type. And in this case, triatomic, you get so many, total 6 number. Now, if you take tetratomic, pentatomic, and all, you get more and more number of vibration mode. Acha, out of this, suppose carbon dioxide is doing like this, scissoring action. So what will happen? Originally, carbon dioxide is a linear molecule. O double bond, C double bond, linear. straight, or carbon dioxide is linear molecule, and it has got a dipole moment 0. Sure? Dipole moment 0. C O double bond C double bond O. Both sides the oxygen is there, and the electron attraction of electron is equal in both sides. That's why it will be dipole moment will be 0. Now when it bends, then dipole moment will be there. When it is straight, there will be no dipole moment. But when it is bent, then there will be dipole moment. So as a result, the dipole moment will be created, which is called fluctuating dipole moment. In one moment there is dipole moment, in next moment there is no dipole moment. That is called fluctuating dipole moment. So that sort of phenomena should be there, then only that molecule will be IR active. And your question will be, when the molecule will be IR active? The following some options given. Which of the following will be IR active? CO2 will be IR active, CH4 will be IR active. Because CH4, you know, it is dipole moment 0, but when it bends, dipole moment is non-zero. So 0 and non-zero fluctuation will be there. So this fluctuating dipole moment is the major reason for IR absorption. Why does it happen? When the molecule vibrates, the particular IR frequency matching with that vibration frequency, then only it absorbing and giving some sort of resonance. You understand resonance? Not chemistry resonance, physics resonance. One wavelength is propagating, another wavelength is also propagating, superimposing one upon another. What happens? Resonance phenomenon. Enhancement of amplitude. Follow me or not? বুঝতে পারছি না? So physics resonance বলতে কি বোঝায়? One wavelength is propagating like this, another wavelength is also propagating like this, and both are superimposing on each other. Otherwise it can be, there are two options. Either it will give this superimposition will be constructive and it will give you resonance, amplitude will be enhanced. Otherwise it will be damping vibration. The amplitude will be 0, isn't it? So that type of phenomena, molecule is absorbing IR radiation, enhancing its own movement. Molecules are absorbing IR, and by absorption it is enhancing its own vibration. That is happening. Now nowadays the instrument that is used is called FTIR, Fourier transform IR. What is Fourier transform IR? I will give you some simple idea. An IR and UV, there is a basic difference. In case of UV, we are using solution because we have cuvette and put there. But in this case, for IR, we can use solid sample also. Solid sample. And we don't put it in the cuvette. There is a chamber, we put the pallet or tablet there. Now, how the tablet is made, that is also another story. You have to take KBR. So, and in that, you take very small quantity of the sample. That means dilution is necessary. For UV, we are diluting with solvent. And for IR, we are diluting with KBR. Solid sample, na? Because KBR is transparent to IR. KBR is transparent to IR. What does it mean? Light will pass through without any problem. KBR is transparent to IR. That means IR can easily pass through without any or much of absorption. So that's why it is called IR transparent. So it is IR transparent. So you take KBR and a very small quantity of the sample, mix very thoroughly, quite thoroughly mix it, grinded and mixed together into the mortar pestle, particularly if required. And after that, there is a compressor where we press it to make a tablet. This we have done actually. Okay, so these things are mixed together, blended together, grinded and blended together, and after that we make a press to make it a tablet. And that tablet will be looking very nice, transparent tablet, and in that the sample is there. It is inside, this sample is there. Put it inside the chamber and light will pass through. After that you get the spectrum. So it is applicable for liquid. It can be, sometimes we take some oil. It is called muzzle oil, lubricating oil type of thing. With that we take the sample mix it in that oil, okay, and then it is used. So different ways, sample preparation itself is a story. Okay, different way, different sample we will have to prepare in different way. Solid sample, liquid sample, all these samples are can be analyzed here. Sometimes, always it is not possible that you dissolve in the solvent, right? So here you can use it solid also. Actual spectrum looking like this. So clumsy, isn't it? The bottom one, see, so clumsy. But this here, this particular region, what is the region? 600 to 1400. In this region, centimeter inverse, maximum number of peaks are obtained. You can see the whole spectrum. If you see, this is not much interpretable, isn't it? You cannot make any claim. You are getting certain peak here, but this position, can you claim anything? No. But here you got lot of peaks, and this region is called fingerprint region. What is a fingerprint? It is specific to a person. Our fingerprint is very much specific. So one fingerprint does not match with another one's fingerprint, right? So here this molecule also has got a fingerprint. This molecular fingerprint is detected by IR, and so this particular region you get lot of peaks, and every peak it is already mentioned what peak it is. C double bond O, C double bond C. The peaks are here. These double bond peaks. Okay. So these are IR absorption bands, and the peaks are interpreted over here. The interpretation is there in front of you. This is the interpretation.
In this online lecture, we're going to discuss the basics of IR spectroscopy. We're going to see how the machine operates and how it delivers its data. 2, a functional group will absorb light if the frequency of light matches the frequency of stretching, bending, or wagging. This is going to be our most important key point. This is the basics of how the IR machine functions.
It's a very important line. Just read out this line. A function group will absorb light if the frequency of the light matches the frequency of stretching, bending, or wagging. As I was telling again, okay, so I already told you, now you can consider this a revision. So the molecule will absorb IR radiation if only its own vibration frequency matching with that IR radiation frequency, otherwise not. Molecules are all vibrating with certain frequency. That frequency and the frequency of IR radiation, if they matches, then only the absorption will occur, otherwise not. Whenever you put certain light, there is no guarantee the matter will absorb it. It will absorb if there is a purpose. Molecule will absorb only if there is a purpose. Ultraviolet radiation you have given, so molecular electrons can be promoted to higher energy level, for that is the purpose. That's why molecule is absorbing the UV and visible radiation. The electrons are getting promoted to the higher level. It can absorb IR because the function groups are absorbing, and function groups are having certain bending, stretching type of vibrations. That frequency and the IR radiation frequency matching. That's why it's absorbing. Okay? Why molecule will absorb microwave? Molecules are having some rotation. The rotational frequency and the microwave radiation frequency matching. Then the molecule is absorbing the rotational frequency. Are you getting it? So why molecule will absorb that microwave? Because its rotation is matching with that. Why molecule will absorb IR? Because its vibration is matching with that. Why it will absorb the UV or visible? Because its electronic transition is matching with that. So specific region it will absorb the radiation, not in general. The specific value it will absorb, and from that specific value analysis we can say about the molecule. That means what is there in the molecule that you can claim, we can comment, we can predict the structure of the molecule. Sometimes the molecular structure is so complicated. Think about the alkaloid. Have you heard about alkaloids? কি বলো তো? What is alkaloid? না বোধহয় জানো না. Alkaloids is a milk-like material obtained by breaking some of the plants. If you break the plant, twist the plant, some milk-like material comes out, colloid type, colloidal liquid, the white color milk-like liquid comes out, that is called alkaloids. And these alkaloids are sometimes medicine. These alkaloids are sometimes useful. One of the alkaloid is mostly used for our purpose. We are using it. Can you tell me what? One type of this alkaloid that we are using a lot. What? What alkaloid? Rubber. Yes, rubber. Let's talk about rubber only. That is huge quantity that is extracted rubber. Okay, that is also alkaloid. Now there are so many different alkaloids.
And lastly, what we're going to see here is that 3 IR spectra show absorption bands that enable to determine if a certain
See,
functional
the point number 3. Different functional groups, first point, different functional group bend, stretch and wag at different frequency. And last point is IR spectra show absorption band that enable to determine if certain functional groups are present in a molecule. That means certain functional groups is there or not. Okay? If you can get that, you can get the idea the molecule is actually acid or alcohol or amine. That idea, preliminary idea we get by this IR. Because if you can detect the functional group, rest of the things are easier. If you can detect all the functional groups of a molecule, rest of the things will be easier. So this IR gives us what? Information about the functional groups.
of a dog. And then let's represent it. We call that an IR spectra show
Start from here.
absorption bands that enable to determine if a certain functional group or groups are present in a molecule. So let's see how this works. What you see here is the molecule formaldehyde. And formaldehyde just so happens to have something called a carbonyl functional group. That is simply the C that's doubly bonded to the O. We call that a carbonyl functional group. What we need to understand is that if you actually have a sample of formaldehyde, it's
What is
not-
this compound? What is this compound? Namta bolo to? Formaldehyde. Formaldehyde. Okay. And so this functional group C double bond is called carbonyl functional group. Carbonyl.
Static like what you see here. For instance, let's represent the oxygen right here as some kind of sphere and the carbon also as some kind of sphere. And the double bond between them, let's represent it as this single bond right here. If you were to actually see a formaldehyde molecule, you would actually see the carbonyl bond do something like this. It would actually stretch and compress like this.
These stretching
Almost
vibrations.
as if there is a spring between the carbon and the oxygen. But that's not the only thing this carbonyl can do. It can actually do something like this, move back and forth like this. In organic chemistry, we call that wagging, kind of like the tail of a dog. So this is the reality of the carbonyl group in formaldehyde. What we've seen is that it can stretch, or have what's called a stretching vibration. And let's do this. Let's make up a number. Let's just say it happens to stretch at a frequency of 2 hertz. Now, what does that mean here? Remember, hertz is a measure of cycles per second. So if this is stretching at 2 hertz, it basically means this right here. Let's say we start at this position. The 2 hertz means that it'll stretch 1 like this, and then 2 cycles per every second. Now, keep in mind that's not the reality. It actually vibrates at a much, much higher frequency, but let's keep the number simple for now. And also, just a side note here, of course the vibrations would be temperature dependent, but let's just assume room temperature for our example. Now, let's say we also measure the wagging, and let's happen to say that it wags at 4 hertz, which again, it means it goes back and forth 1 cycle, or wags back and forth 4 times per 1 second. If that's the reality, then let's see what happens when we take our formaldehyde molecule and we stick him in the IR spectrometer. And let's again label our stretchings at 2 hertz and our waggings at 4 hertz. So here is how.
So you ask now why OH is actually some protein. Just see the molecule that particular functional group is doing like this as well as doing like this. So for this one, it is giving accepting certain energy, and for this type of movement also it is certain energy. So that way, if these things are combined, it gets product.
How the IR spectrometer functions. What happens is when the molecule is in the machine, we take something like this, a light source, which is simply something that has the ability to shine light at a molecule at various frequencies. On the other side of the machine, we have this thing right here, a detector, and all he can do is detect light. Now, imagine this for a second. Let's say again, our light source has the ability to produce light at various frequencies. So let's say we set our light source to deliver a light that happens to have a 1 Hertz frequency. If we shine this 1 Hertz frequency light at our molecule, it'll go right through the molecule and hit the detector. And the detector, of course, would say, when you shine 1 Hertz frequency light at the molecule, I detected it. We'll see why that happened in a second. But for now, let's graph what we see in front of us here. If you had a graph with, let's say, on the y-axis, the percent transmitted, and this means the percent of light that transmits or moves through the molecule, which would obviously run from 0 to 100%. And let's say, for now, on the x-axis, you put the frequency of light. So the graph of what we just saw here would look like this. At 1 Hertz frequency light, 100% of the light went through the sample, and the detector detected that light. Now, let's see what happens if we go back to our light source, and now let's set it at 2 Hertz frequency light. If we shine this at the molecule, what's going to happen here is the molecule will actually absorb light at that frequency. And this right here is key to understanding how this machine works. Notice the frequency of the light that's being absorbed, 2 in this case, matches the frequency of the stretching. When these two things match up, the molecule will absorb the light, which means think about the detector here. His observation is that when you shine 2 Hertz frequency light, he doesn't detect the light at all, because it was simply absorbed by the molecule. Let's see what this would look like on our graph now. Again, at 2 Hertz frequency light, the detector would say not very much transmitted through it. A lot of it was absorbed. So we have a small percent that's transmitted. And that would be this point on the graph. Now, let's go back.
So this is the reason we get the plot, the peak. Okay, sometimes the molecule is absorbing, sometimes it is not absorbing. If it is not absorbing, directly we are getting in the detector. But if it is absorbing, okay, then you are not getting the light in the detector. And detector is simply a system, it is a type of photovoltaic system, suppose photovoltaic detector. So what it does, whenever illumination is done, the light is falling onto that, it will give the current flow. And if the illumination is not there, it will not give the current flow. So simply from the photovoltaic detector also you can decide that how much current is flowing and how much current is not flowing. Accordingly you make a plot and give the spectrogram. And absorption is happening whenever the molecular vibration frequency matching with the IA radiation frequency that is coming from the light source. It is absorbing. Otherwise it is not absorbing. Okay.
To our machine here, let's now take our light source and set it at this time 3 Hertz. Think about what we just learned here. If this molecule stretches at 2 Hertz and waves at 4 Hertz, then when we shine the 3 Hertz frequency light, it should go right through it.
No absorption.
There's no match in this case.
3 Hertz no absorption. 1 Hertz no absorption. 2 Hertz there was absorption. 3 Hertz there is no absorption.
So again, going back.
Now again 4 Hertz.
Right here,
Now there will be again
you see
absorption.
that this would be the graph.
So you give it another
3
peak.
Hertz frequency, 100% transmitted.
Understood
Now,
this?
over here,
So I will
let's-
just skip. Okay. So this I wanted to show you. But if I tell again and again, maybe it will not go to your mind. Now it should go. With graph it is plotted, na? So first 1 Hertz when you are passing through, no absorption. Because the molecule having a frequency 2 Hertz. Now 2 Hertz is going, then is absorbed. So it is falling. Because it is totally absorbed, So in the detector you don't get any light, or if there is a, it is very little light. And after that 3 hertz if you give, then again there is a no absorption. So again 100% emission. So that way it works. That way it works. So molecule, different type of frequencies are there. So that way, it may absorb, it may not absorb. Accordingly, get a plot, and from the plot, the different frequency that we obtain, we can decide what are the groups supposed to be present. Suppose we have got 3000 around, that is which group is present. 1760, 1770 type of frequency, that wave number. Then you can decide, well, so there is a C double bond group present. So that way the functional group is detected. And that way you can identify the compound. Okay? C double bond 1717. So the different, you will have a huge chart. If you see in the Google also, you will find lot of charts are there. So every function group has a specific position. That at particular which wave number the absorption will occur. So that way you can detect impurities. Impurities into drug, impurities into food, some fertilizer, pesticide, what type of fertilizer is used into the crop field, what type of pesticide used in the crop field. This type of you can get some ideas. Not always so easy, but some of the things it can be done. So the second is protein quantitation, means quantitative way, the protein structure, analysis of the protein structure, which is very complicated. So by the spectroscopy, we can get some information. Isomerization in organic chemistry, different type of isomers, okay, analysis of isomers, mechanism, there is a role, mechanism, how the reaction is happening, the mechanism. Progress of a chemical reaction, that I was talking mechanism. Mechanism is progress of a chemical reaction. How the reaction is happening. In between, what are the groups produced, whether there is a transition state or intermediate. This type of information with the help of IR spectroscopy or all the spectroscopies in general, we get information. Otherwise, you can claim that arrow, you are giving arrow. This is opening, this is closing, this is happening. But how do you prove that? Mechanism you have heard, na? You have seen mechanism. So you are giving arrow. So this bond is breaking. Now it is attacking here. But that is your just claim, your idea. It may not be true. Isn't it? So how do you prove? And nothing is until and unless it is proven. Science will never accept that. You have to prove. So this different spectroscopic technique helps us to prove lot of things. How the reaction happens, how it is happening, mechanism, first order kinetics, second order kinetics. So we are talking about things. You have to prove it, na? So that spectroscopy helps us a lot. Got it? Forensic and allied applications. There is a murder, suppose. Okay, so there is in the wine glass, there is a fingerprint, and in that there is a smell, some sort of peculiar smell coming out. That smell is giving some doubt that it may be some sort of poisonous potassium cyanide or something like that. So potassium cyanide has got certain smell. So cyanide smell is coming. So but okay, you can doubt. Can you prove? If you cannot prove, nothing is accepted in the eyes of law. So in the court, if you just say so, I got certain smell, nobody will accept that as an evidence, isn't it? So there, spectroscopic techniques are quite helpful. You have gotten some oil painting. Okay, oil painting, and you want to know what is there behind that painting without damaging the painting. Directly not possible. You can do the spectroscopy. You can get some information. You know Da Vinci Code. Have you heard about Da Vinci Code? No. Mona Lisa picture of Leonardo da Vinci. So that picture probably was made on another picture. So what is there in the picture behind that you cannot see from now, but with the help of spectroscopic technique you can get the idea that what was there. So digital. Spectroscopy and computation. Only computer cannot do everything. Some taking different helps. Lot of applications. And what is FTIR? I have not completed yet. I will tell you. IR you have heard, understood. What is IR? What is IR? At least you understood. Now, what is FTIR? Fourier transform is a mathematics. Fourier transform is a mathematics. And physically, what is supposed to be done? We have a plate. Suppose there is a plate, and you cannot damage it. It is something ancient, which is very, very costly, and there is no unlimited value actually. Very precise or priceless. So in that case, what you will do? You cannot break it, but you want to analyze. Then what to do? So there spectroscopy can help. And then FTIR doing what? Light coming in, knocking and then going back. Because this plate is not transparent, so it will not pass through. Light will not pass through. Will be reflected. Let it reflect again and again and again from the surface. After that, we will analyze it. That is FTIR. Okay. It is not always necessary that light should pass through. If light does not pass through, then what do we do? FTIR will do. Light will come, reflect from the surface. Repeatedly it will be reflected, and that reflected pattern of light will be analyzed by FTIR. Okay, time is up, so I close it here.